Hello everyone, I am Saptami Hegde, a PhD student in Institute of Biophotonics in National Yangming Chiaoteng University. I am pursuing my PhD under Professor Surojit Chattopadhyay. Our laboratory is called by the name Functional Nanomaterials Laboratory. I am currently working on fabricating a perovskite-based photodetector. In this presentation, I will be talking about 2D mixed 3D metal halide perovskites, their properties and applications. In the upcoming slides, I'll be introducing you about perovskite and its general crystal structures and elaborate on the structure and applications of a special class of perovskites known as organic inorganic halide perovskites, also known as OIHPs. I'll be briefing on the reports of stability of these perovskites and proceed to discuss about my research work, starting from motivation for the current research objective, the current research plan, the initial results that I've obtained so far, and future directions on this work. Let's start from the basics about the crystalline structure of perovskite. So perovskite is a crystalline material with the generic formula ABX3, where A, B are cations and X is an anion. Here you see a graphical representation of the crystalline structure of three-dimensional perovskite. These black spheres here are cation B, the central one is cation A, and these green spheres are anion X. If we consider this cube where the black spheres are the corners, you can see that each of these black spheres, that is a cation B, is coordinated with 6 anions. So this BX6 can be represented as an octahedron in this way. So this is how we can visualize the 3D crystal structure of a perovskite. One unit cell, that is along this part, is shown here, where the corner shaded ones are cation A. It could be here, 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 and here, like shown here. And one unit cell consists of one octahedron, and the corner ones are the anion X, and the central one is the cation B. So based on the composition of A, B, and X, they have various applications and are classified into various types. So perovskites find applications in various fields like solar cells, superconductivity, catalysis, and spintronics. And based on their composition, they are of various types. If they are oxides, hydroxides, silicates, fluorides, and arsenides, these are natural occurring ones. And among the synthetic perovskites, they could be metallic perovskites if the cations are metals. They could be completely devoid of metals and have only organic compounds, organic cations. So in such a case, they are metal-free perovskites. And there's another type, a hybrid of organic and inorganic, where one cation could be organic and the other cation could be metal. So those are known as organic inorganic hybrid perovskites, and I'll be talking more about these. In specific, a variant known as metal halide perovskite. So more about the structure of OIHPs. We have the generic formula ABX3, where A is an organic cation like methyl ammonium or formamidinium. B is a metal cation like lead or tin, and X is a halogen ion like bromide, chloride, iodide. Some typical examples would be MaPb, Br3, or FaSnI3, FaPbI3, and so on. OIHPs might have another organic cation known as A dash, and this has a longer alkyl chain compared to this organic cation A, which is a small organic cation. When we introduce another long chain organic cation A dash in ABX3, it results in different dimensionality in the resulting perovskite structure. So these are the various structural possibilities of the OIHPs. So the typical 3D perovskite with the formula ABX3 would look like this. One unit cell is blown up and shown here with A, B, the B and X. And then in case if all the A were replaced by A dash, then we would get a two-dimensional perovskite structure with this formula. So in between the octahedron layers, we have an organic layer. If it consists of A and A dash, we have an intermediate phase between 3D and 2D perovskites known as the quasi 2D or the 2D mixed 3D perovskites. 3D perovskites have growth in all three axes. 2D perovskites have growth only in two axes, whereas the intermediate one could be a mixture of 3D layers separated by organic layers, just as in the case of 2D. There are also other dimensionalities in perovskites like one dimension perovskite, which have completely different chemical makeup or structural formula, and these grow only along one direction and they have dangling bonds on either sides. And then there are zero dimension or perovskite quantum dots, which are just separated unit cells of the 3D perovskite structure. Let's move on to properties and applications of OIHPs. Three-dimensional perovskite structures, the metal halide variants, are exceptionally known to have remarkable optoelectronic properties which are also tunable, and this makes them as perfect candidates in solar cells and photodetectors. This is an example of one perovskite FAPBI3 being used in a solar cell. This is the general schematic and its SCM image of different components. The same has also been used in a photodiode, which is a photodetector. This is the general schematic of the photodiode, the work function of various components that make up the photodiode, its electron microscope image, and then we have this current density versus voltage plots, which are characteristics for a photodiode. So FAPBI3 is successfully incorporated in a photodiode. But these materials have one shortcoming, that is, the 3D perovskite structures are unstable, they are prone to degradation. Now let's dig into why and the hows of the instability in perovskite structures. Why are 3D metal halide perovskites unstable? Here is a typical example of a 3D metal halide perovskite MAPBI3. You see these octahedrons? So these are the PBI2 octahedrons, where these purple spheres are the iodine atoms. So there are 6 of them in one octahedron, and in the center we have the metal cation, that is a lead cation, and between those octahedrons we have this small organic cation, methyl ammonium. It has one carbon atom, one nitrogen atom surrounded by 6 hydrogen atoms, and one of these hydrogen atoms is linked to the iodine atom, which forms a part of this octahedron. So when we realize this in a 3D form, this is how it would look like. So the intact 3D crystal perovskite structure is known as alpha perovskite. And when such an alpha 3D perovskite is subjected to intense light or high temperatures or heavy moisture content, the organic components in them disintegrate. So in this case, Ma disintegrates as CH3N2, and this H along with this I leaves the crystal as Hi gas. And this I is also removed since there is a neighboring Ma cation at this position. So what we would be left out is these PBI2 octahedrons with gaps between them, which is visualized this way. So this is the PBI2 phase, or in other words, the degraded phase, which is also known as the delta phase of a perovskite. So alpha phase is the intact crystalline structure of a 3D perovskite, whereas delta phase or the PBI2 phase is the degraded form of the 3D perovskite. We have to combat this degradation issue so that they can be successfully realized in solar cell and photodetector applications. So there are some reports on enhancing the stability in 3D perovskites. One of the simple ways is to replace the Ma organic cation with a slightly more stable Fa organic cation. Fa or formamidinium organic cation has 2 nitrogen atoms, whereas methyl ammonium has only 1 nitrogen atom. So if we replace Ma by Fa, the resulting perovskite structure would be slightly more stable. Other means of greatly enhancing the stability would be through pseudo halide or super halide substitution, where Some groups known as a pseudo-halide like SCN, that is thiocyanide, or superhalide species like the BF4 or PF6. The name is superhalide because they have more number of halogen atoms, 4 fluorine in BF4 and 6 fluorine in PF6. So when these groups replace the parent halogen ion in the 3D perovskite, the resulting perovskite structure is more stable. An example is given here where FASNI3 is being used in solar cell. So the original FASNI3's 3D perovskite crystal structure looks like this. When the iodine is being replaced by pseudo-halide SCN in increasing amounts, we see that the crystal structure of the resultant perovskite changes. In this case, where all of the iodine is replaced by SCN, we have a highly stable structure. In this work, a solar cell is fabricated and compared between this structure and this structure. So when the pure 3D FASNI3 was used in the solar cell, in the graph normalized PCE versus time, we see that the PCE value drops down after a few hours. But if this structure was used, we see that the normalized PCE values are stable even after longer hours. So which means that if we use this structure, it is more stable in a solar cell compared to the pure 3D FASNI3 structure. Another means of enhancing stability is to introduce the A-bulky organic cation in the ABX3 structure. So in bulky organic cation, there can be two types of cation. The monovalent cation having one NH3 plus group and the divalent cation having two NH3 plus groups with the organic alkyl chain. So this modifies the 3D structure into a 2D mixed 3D structure, as I discussed in one of my previous slides. So one of these material was used in a solar cell. So the 3D was FAPBI3 and this was doped with a monovalent cation, and the resulting perovskite was a 2D mixed 3D perovskite. And when this was incorporated in the solar cell was found to be more stable against moisture and air. So what if we could also fabricate photodetectors which are stable? So this is the motivation for my current research work. Before we move on to the details of my research work, some more points about the bulky organic cations. If we dope the 3D perovskite with monovalent cations, we would get RP phase or Rudelson-Popper phase perovskite. You see the alternating 3D layers here, which are separated by the spacer region, which is composed of monovalent cations. So these cations head group forms hydrogen bond with the iodine atoms in the 3D layer, whereas they are linked to each other via van der Waals force, which is a weak force. Whereas in case of divalent cation, which is known as DJ phase or Dion-Jacobson phase, the two head groups are involved in hydrogen bonding with the alternate 3D like layers, and we see that the spacer region is shorter compared to the RP phase. And also from these arrows you can see that there's a misalignment in the alternating 3D layers, whereas there's no misalignment in the alternating 3D layers. So it's safe to say that divalent cations incorporation results in a more stable structure than monovalent cation incorporation. So I plan to use the divalent cation substituted FAPBI3 perovskites in fabrication of a photodetector with high performance as well as enhanced stability. So this is the objective of my current work. A simple research plan. So our lab expertises in growing monolayer graphene on various substrates. So I choose a suitable solid substrate on which I grow an almost monolayer graphene using CVD technique, and then keeping a mask on the graphene layer on the substrate and depositing metal contacts, we obtain a simple coplanar device, and I use this device as my photo detector on which I drop and grow perovskite films and characterize these for broadband illumination, that is, lasers of various wavelengths. Before moving on to the synthesis and other aspects of the perovskites, let me tell in detail how we can incorporate the bulky organic cations in a 3D perovskite structure. We have the 3D perovskite structure, which has low structural stability but has outstanding optoelectronic properties, and then we have the 2D perovskite structure, which has high stability but its optoelectronic properties are poor compared to 3D. So if we get an intermediate form of 3 dimension and 2 dimension, it would look like the one that you're seeing here. So it has alternating 3D like layers separated by organic spacers. How would we achieve this? By increasing the concentration of organic cation starting from 3D. So we take a 3D perovskite like FAPBI3 and then dope some concentration of bulky organic cation in it, which is divalent. So we get 2D mixed 3D intermediates, and if we increase the concentration of the bulky organic cation, we would end up with a fully 2D perovskite. So we only increase the concentration of the bulky organic cation enough to get the intermediate phase of 2D mixed 3D phase. And based on the length of the cation spacer between the alternating 3D like layers, we can assign different numbers based on the number of layers in these perovskites. For example, 2D perovskite would be called n is equal to 1 because it has one octahedral layer separated by the organic spacers. N is equal to 2 is a 2D mixed 3D which has two octahedral layers separated by the organic spacer. 3 has 3 octahedral layers, and so on. If there is no organic cation spacer and the octahedral layers were continuous, then the number of layers would be infinite, and this is the case of a 3D perovskite. So now talking about how I synthesized these 2D mixed 3D perovskites in lab. So I took the iodine salts. So in FAPBI3, I is the halogen atom. So I took iodine salts of the divalent bulky organic cation, iodine salt of formamidinium cation, and iodine salt of lead metal. I combined them in various ratios in the solvent DMF in order to get perovskite precursors of various N layers or N values. Next is we grow a film using these precursors on suitable substrates. I chose my substrate to be quartz since I intended these for optical characterizations. So after UVO treatment of the quartz substrate, I drop about 40 microliters of these precursors and then anneal them at higher temperatures in 2 steps in order to obtain perovskite film on the quartz substrates. The resulting perovskite films obtained from various precursors look this way, and their corresponding N layers or the 3D and 2D are marked. And now I perform optical characterization, that is, I obtain the absorption spectrum as well as photoluminescence of my perovskite samples. So let's have a look at the absorption spectrum. So here is the reference from another paper about pure 3D FAPBI3. We have its absorption spectra as well as PL in the same image here. So if we observe the absorption edge, it's beyond 800 nanometers. But in our case of 2D mixed 3D, ranging from 2D, that is this black line, to pure 3D, which is this olive line, and the intermediates between, we see that we can control the absorption edge of the perovskite films. It ranges from below 500 to 850 nanometers. Same also goes for the photoluminescence of the perovskite films. We see that the PL peak in the pure 3D case in the reference is shown to be beyond 800, and in my case of perovskite samples ranging from pure 2D to pure 3D with intermediates in between, we obtain a tunable range of about 300 nanometers. So I have demonstrated that 2D mixed 3D perovskites can be synthesized by doping FAPBI3 with various concentration of bulky organic cations, preferably the divalent ones for higher stability. And I have also shown the tunability in the absorption in PL of the perovskite films I have grown. In the future, I'm going to further characterize these samples in a synchrotron facility, and after enough studies, I intend to use these 2D mixed 3D perovskites in fabricating a photo detector device aimed at high performance with augmented stability. Thank you.